Welcome back. Brand new day, brand new week. Microphone closer, and thus hopefully clearer and less noisy. Maybe that'll fix it. So last time we were talking about the representations of SL2C, and let's keep doing that until there's other questions from chat. I just got to get myself sorted out here. And it won't be. Oh, good morning, Nicole. First in chat today. Yeah, we'll have a longer one today. Not longer than usual, but I mean closer to our 40, 60 minute mark. Last couple days were I changed my clock. Suddenly my streams are an hour earlier. That could be. Wait, daylight savings was a while ago. I mean, the thing is, my streams are never really at a very particular time. They're basically when I do them, and that is sometimes at 7:30 my time, and that is sometimes at 9. But definitely for the next 3 weeks, they're probably going to be around this time because I'm participating in some program for mathematicians. Yeah. Good morning, Edit Smith. What am I saying? Fancy stream thumbnail. Yeah, I actually many years ago, before this channel was even close to being monetized, I paid someone way too much. Well, not too much money, I should say. It's definitely a fair amount, but too much money for what I could afford at the time to make that banner for me. Could I suggest some topology material? I could. Mainly practicing questions. Turns out I am not too good at maths, but it's way too late to change my major. Oh, nice, Yaman. Well, there will be more SL2 reps in this video. Don't you worry. But let's talk about topology first. So there is actually a book. Practicing questions. I mean, Munkres, I think, is a great text, and it has lots of exercises. So, oh, you thought it was AI? No. Jeez, yeah, everyone thinks everything's AI these days. There's actually a really interesting video from Hank Green talking about how there was some like rocket launch in China or something, and there's this like really cool drone footage that speeds up and slows down, but then, everyone was accusing it of AI, even though it's not, just because actually the video quality is like so good and it's such like a crazy shot you normally wouldn't get. We're really living in a crazy world where we can't even tell anymore. None of us that study maths are good at maths. Yeah, exactly. We're the ones that really don't know math. Yeah. There's maybe like 3 people that sort of know math, and they all have Fields medals. Well, maybe more than 3. But mind you, probably most of them would say, closer to the mic, yes. Wait, you're commenting. You're not telling me to go even closer, right? I mean, I don't think I need to be this close the entire time. Munkres, there's also a book. Look, I haven't read it, so I should not suggest it to you. But there is a book called Counterexamples in Topology. And that is maybe not a bad idea. Though I haven't read the specific book, one of my words of advice to students is always, whenever you come across some new concept, make sure you always have at least one example and one non-example on on hand and together with proof. So like, I don't know, you come across the concept of Hausdorff, you should be able to, on an exam, immediately bust out, the proof, say that Rn is Hausdorff, and the proof that the finite complement topology on an infinite set is not, right? Those are two, like, classic examples. It doesn't have to be those examples. Turn up my browser's volume control. Wait, really? Hang on. I'm just going to turn up the volume on my mic, because I'm not really going to put my mouth right on the fuzzy thing the entire time. Was it just too quiet? Is that the only issue that you guys were having? Is spec of kx localized at x to spec k a morphism of finite type? Well, let's find out. Let's find out. Analysis was fine, but somehow not able to do topology questions. You're kind of fine with the material covered. You were fine until analysis. I see. Yeah, I'm not sure. I mean, I guess, yeah, the thing is topology is maybe more formal because you don't, topology is more formal because maybe you don't have the same sort of tools to lean on with, like, metrics and stuff. Oh, duck with a monocle. Oh, okay. Should I? Is the volume too high now on my mic? Whatever. It's probably good. Someone will yell at me if it's not good. Yeah, nice book. Didn't read it all, but remember it during your topology course. Yeah. So I mean, okay, probably counterexamples in topology is still a good resource for you then, because, well, whether they're examples or non-examples, there's going to be a lot of content in there of putting some of these proof techniques into action. So yeah, perhaps that would help. Perhaps that would help to see a lot of those proofs. Okay, so we got spec of kx localized at x. I guess I'll put it here. Right, so we've got our natural inclusion into this ring, and we look at the corresponding map of schemes, and we want to know, is this of finite type? So I believe finite type, right? That's like locally, it makes the one module into a finite type module over the other thing. Let's look up our definition here. Yeah, I went to Wikipedia instead of Stack's project. Sue me. Yeah, and I think for this case, because so for an arbitrary scheme, we need to check this on all the affine opens, but because this is an affine scheme, it suffices to just check the ring map. As finitely type if B is finitely generated as an A algebra. As an A algebra, right. So let's see. Is that the truth in this case? Holy Outlook reveal. Yeah. I mean, maybe I shouldn't have showed you my emails. Well, if you hack me, good job. We all know why. Yeah. So we just need to know, basically, is kx localized by x a finitely generated finitely generated K algebra. And sure, right? I mean, if we're localizing at the ideal x, this is basically just things of the form. Oh no, is it? So we have f over g, and basically x does not divide g. These are our polynomials. Yeah, glad to be back. Glad to be back, Nerd Coke. Or am I? The mountains are nice. Should have stayed there. Finite type, if it's finitely generated as an A algebra. Right, so... yeah, I guess... Certainly, if we think about our terms in the numerator, those will all be taken care of by these terms, just by x. So we have that much. Things get a little weirder in the denominator, right? Because we precisely don't have x downstairs. So what would be our... We need to come up with some finite generators downstairs. Surely it must be, right? I mean, surely it must be, because this is... I mean... Surely it must be. But what do we want to take for generators? I mean, Deepak, the thing is, that is very strange, because I don't think anyone else is having this issue. And I've not noticed this issue when I've like gone back to click on videos when I, put the topics in the title later. I guess we've probably got to do some trick with this ideal, right? Maybe if we do some sort of like GCD type business. Because everything outside of this ideal. I mean, naively, one thought as well, we just have like, x plus k as k runs over the entire field in the denominators. And that should be enough to generate everything. But of course, if k is an infinite field, then we run into problems. So perhaps it's not. Perhaps it's not. But then again, surely, I mean, x plus a, x plus l. Okay, well, have fun. Enjoy your category theory problem set. Thanks for joining. Yeah, I'm being really dumb. I'm gonna cheat. Well, now you see my French learning videos as well. Everything's getting exposed today. let's see. Localization map finite type. But I'm not reading all this right now. Ah, here we go. It is not finite type. Aha, I see. Since it's not finitely generated as a module. Yeah. So it does look like those denominators are a problem. Does look like those denominators are a problem. You're told it's not a finite type. Yeah. So how do we rigorously prove this? Yeah. I mean, so I guess I was right. My suspicion was right. These things in the denominators, that's kind of the problem. So I'm guessing we could engineer a proof with this, right? Yeah, we should be able to engineer a proof with that somehow. Because certainly, right, we need some sort of list of generators. Say finitely many generators. You know, proof by contradiction or something. Now I wonder. Like somehow I want to use the fact that X is a generator for KX, right? So basically I want to say that we could clear numerators. We could clear numerators somehow. And I think this is the case. Let's see. Yeah, I think I'll just leave it as a proof sketch for now instead of sitting and thinking on live stream. But I think somehow this is the idea. You need to assume there's a contradiction, probably because the issue is we have at least if K is a infinite field. We're going to have infinitely many terms like this. And, you know, how are you going to create those terms? You know, if you try and add two polynomials together, or two rational functions together like this, we'll get something like this. And, I mean, it's not so clear that's a problem, right? I mean, this is increasing the degree of what you have in the denominator. But yeah, so I suppose for each K, you know, you assume that you have some linear combination, some K linear combination of these things, right? So it'd be like 1 x plus k, call it a1k. Maybe we'll keep the dependence on k and get some contradiction there. And then which way could we multiply it? I mean, we'll have something like x over k equals, and then down here we'll have a product of g1 to gn. Up here we'll have some, oh, sorry, that should be g1. This be a1k, and maybe call it, I'll call it g1 hat to mean this is the product of all the g's except for g1, right? So g1 hat f1 plus a2k G2 hat, which means all the product of all the G's except for G2 and so on. Gn hat. Yeah. Okay. Now, why should that be problematic? Probably we could contradict some degree counting thing, right? So over here I have some product. This will be x plus k, and this will be a1k. I mean, just the same thing as above, right? And now probably I think probably there's something like the degree on this side here is going to be the sum of the degrees of each of the GIs. This will be 1 plus so I guess the degree interesting. Yeah, so maybe we could work out some contradiction here, because this is almost like the GIs. This will be very close to the correct thing, but then we have FI here, and so or whatever is like this will be 1 plus the degree of the max of each G, GI, FI. I have no idea if I'm going in the right direction. I said I wasn't going to do this, and then I just started randomly following my nose here. So let's say for some J, this is the maximum. Right, and I guess actually, so I guess what we get here, this will be the degree. This will just be the degree of GJ left over, because this is additive, so we can pull all of those out, and this should be 1 plus the degree of FJ. Okay, so what does that tell us in this generator of ours? We have some sort of generator with, I guess, the degree of G down here is supposed to just be 1 more than the degree of F up here. Okay, where does that get us? I might have just taken us in useless circles. But my suspicion, my intuition is telling me that somehow we're going to use the degree to contradict it. Let A and B be complex numbers and be fixed. Show that the complex number is a solution if and only if that's a solution. I don't know if I really want to do that. Okay, I'll put a pin in this. But that's my initial thoughts on this question. Probably somehow you want to play some game with the degrees like that. That's my guess. Maybe contradict that one is the maximum or something. I don't know. Probably. Yeah. Anyways, okay, I'll look at this one. I don't know if I really want to do this. Z4 plus AZ3 plus BZ squared plus AZ plus 1 is equal to 0. If and only if z plus z inverse is a solution to z squared plus az plus b minus 2. Yeah. I mean, I would just start plugging and chugging, I guess. Like, I think this direction's the easier direction, because you basically just plug this into here, into this polynomial, right? Like, so we know that 0 will be z plus z inverse squared plus az plus z inverse plus b minus 2. And then I would multiply both sides by z squared to clear denominators. So this would become z squared plus 1 squared plus a z3 plus z plus b minus 2 z squared. And then probably if you just expand this out, then you get the answer. I don't feel like doing it. I don't feel like doing it because that part's just algebra. I think you should be able to get it. Maybe I'm wrong. But then the converse, I guess, is going to be slightly trickier. Well, no, actually, okay. Probably the converse, actually, if you write this out, you probably get the converse. You just do these steps in reverse, right? It will just, it will just tell you, you basically just backtrack through all these steps because it will give you the trick to how to recombine these things, right? So, okay, as you notice, I have this habit where I say I'm not going to do something, and then I proceed to do that thing. I guess we got to check. Does this look right, though? I mean, this doesn't quite look like what we had above. Oh, no, it does. Right. And then this is exactly the polynomial. AZ3 plus BZ2 plus AZ plus 1. Yep. And so now the converse direction, super easy, right? Because now the converse is just you suppose that this is equal to 0, and now you just walk back up through these steps to demonstrate that z plus z inverse is a root. Yeah, it happens. It happens. I'm sure, I mean, in the same way that you're asking that question, then you're like, oh, it was very easy. I mean, probably this proving that this module is not finitely generated is probably easier than I'm making it out to be. Hello, Luca. Welcome to the channel. And actually, now that I say that, I do think it still has to do with degrees, right? Because so yeah, maybe I'm overcomplicated it by even just trying to focus on this term, because probably if we looked at this, yeah, we could probably prove that somehow we don't get large enough degrees in the denominator. Could we prove that? Yeah, but then multiplication makes things weird. I don't know. Have I had any interaction with the field of algebraic analysis? Always wanted to look into it more after you learned more algebra. It seems really rich. No, I don't think I've heard that term before. If you say algebraic analysis, I just think like functional analysis. Wow. Algebraic analysis. What is this? Not to be confused with the common phrase algebraic analysis of a subject, of course. Linear partial differential equations by using sheaf theory. Okay. So I guess in some sense, I'm not totally unfamiliar with this idea. Oh, hyperfunctions. Okay. Interesting. Oh, it was started by Sato, who actually, is definitely, or Sato. So there's actually a paper by my supervisor and some of his collaborators from like shortly before I got there, which is actually called the Kashiwara, who got the Abel Prize this year. And I forgot to mention that in my geometry talk. I was talking about D modules, and I was gonna say to the geometers, hey, this is kind of what Kashiwara got a Abel Prize for. Well, he got it for a lot of things, but anyways, they have a paper about it's called the Kashiwara-Saito singularity, and it's these varieties I've talked about before in older live streams in my research. There's a particular kind of singularity that shows up that's meaningful for us. And this paper is an analysis of the particular variety attached to the group GL16, which we believe, but I don't think we quite have a proof, completely rigorous proof that that's the smallest example in which it shows up. But, I mean, we have good reason to believe it. So let M be a real manifold of dimension n. How about showing that the quaternions have no zero-divisors? How would I do that? I'll show you in 1 second. Let M be a real analytic manifold of dimension n. X its complexification. The sheaf of microlocal functions, that's a word that means something to me, is given by the microlocalization functor. Uh-oh, someone's getting into a rabbit hole. Oh, by the way, I meant to start playing songs for you every morning about math. So just to add a little flavor, I don't know. Get into a rabbit hole on Wikipedia about micro-local hyper-complex geometry. Hey, hey. So now you can look forward to that most mornings, the 30-second song break. Or could I go back to explaining why we care about Lie algebras? I could. I do have some videos on Lie theory. It's called like Introduction to Lie algebras. It's like a short playlist. FBI transform. That's how you get on a watch list. Yeah, it's like it's a mini list. It's like Introduction to Lie algebras, and I try to give some motivation there. And I think I do mention part of it is we care about Lie groups, but I do try to give some independent motivation. So, yeah, okay. There was a question about showing that the quaternions are has no zero divisors. Yeah, so that's just straightforward computation, and it's gross, but I don't think there's a slicker way to do it. Feel so stupid in here. Feel like you guys know much more than me, and you just started your journey in real analysis. Well, everyone feels like that all the time. I mean, I go to conferences and stuff where I'm also completely dwarfed by super geniuses that are light years ahead of me. And I'm sure there's also people that, you're asking questions about zero-divisors in quaternion algebras, and there's like, I don't know, probably some high schooler in the stream whose like mind is blown by that question. So there's always people above you and below you. But yeah, so for this one, I would just, yeah, I don't think there's any other way to do it but just plug and chug. So literally just multiply these things together, and then so I'm not going to do it because it's awful. It's a nightmare. I don't want to do it. But basically multiply these things out, and of course you'll use your quaternion relations to, you know, determine all the terms. I'll do the first one for you. A times x. That one's easy. And then you'll get a whole bunch of other terms, right? Something you should, you know, write out once in your life. And then the point is, though, that one, I, j, and k form an R basis, right? So the quaternions, they're in algebra, which means in particular it's a four-dimensional. Okay, not all algebras are four-dimensional. This one just happens to be four-dimensional, but it's a four-dimensional R vector space where you can multiply vectors as well, subject to some kinds of relations. So basically what you're going to do is you're going to get terms like this, and you'll get several equations. So I don't know, this will be like ax, what are we going to have? There'll be some other terms here, like minus by. Oh, did I put c here? What a weirdo. This would be z and w. What a weirdo I am. Minus c z minus dw, something like this, right? And you're going to get four equations. And I mean, it can only be, right? It could only yeah. So the zeros come from this, right? And the point is, like, so this will be the stuff times 1, and okay, let me explain it this way. Sorry, this has maybe been a confusing explanation. So when you multiply this out, whatever it's going to turn out to be, you'll get something of the form alpha plus beta I plus j gamma plus delta k, right? And you'll get that thing's equal to 0 once you expand out this product. But because 1, I, j, and k are a basis, the only way that thing could be equal to 0 is if each of those coefficients are themselves equal to 0, right? But if all of those coefficients are equal to 0, then, I mean, each of your coefficients is going to look like this. It'll look like some term like this, and then, like, what is the I term going to be? You'll have ay plus ... something else times I. And so you'll get these four equations that say these things are equal to 0. And then from there, it's just some, like, experimentation and playing around to get some sort of contradiction. Maybe somewhere you break it into cases, right? You could take a case when a is 0 versus a is non-zero, right? Maybe you split it into two cases, and that could help you cook up some contradictions. There might even be subcases. It could get ugly, but yeah, I'm not sure there's a better way to do it. One request. Can I say you can say you can continue your analysis with friends playlist? Well, but unfortunately the my friend why that petered out is he just didn't have the time to commit to it. But that is an idea. I could reboot it. I would need a student who like myself, is not afraid to very, very publicly make stupid mistakes in front of a growing audience of the internet, and both learn analysis. Go through that process together. So maybe, I don't know, if people are interested, if anyone wants to volunteer for that. I don't know how I'd work it out too, because like now I'm monetized, so I guess maybe we like split profits from those videos, but then also like it's kind of like free tutoring, so I don't know. I'd have to think about how to like work out that. You love algebraic geometry, you love the theory of schemes, but you don't see how they're useful, since how you could use them to do math. What problem is solved by introducing schemes? That's a good question. You're not going to do that problem, that's for sure. Why not? I mean, I think you could do it. You gotta, I mean, if you don't, especially, I mean, okay, here's how I know you should try this problem, is because you don't think you're going to do it. You need to, it's like you go to the gym, you got to lift some weights that are like heavy, you got to tear those muscle fibers. So, I think you should spend some time. Doing it. I really do. You think originally you found my channel through my interview series. Do I have others planned? Actually, so some point this week I need to upload. Someone very kindly offered to redo the audio for some of my interviews. So I need to do that. I don't have any planned at the moment. But I probably should get back to doing that, because those are pretty low effort videos. So that's a good way for me to make content without taking up too much time. I do plan to do more interviews. Maybe I should email people. I don't know. I would like to do more. I just don't have any specific ones planned at the moment. But yeah, so I can blab a little bit, but my recommendation to you would be like, look up some of the history of scheme theory. I mean, it definitely allows us to solve new kinds of problems. And define new kinds of structures, right? I mean, so okay, there's a way that you can probe these things. Okay, so here's a maybe some I don't know if this is sufficient motivation, but like for the complex projective space, or the complex Grassmannians, right? For example, these both have manifold structures to them, right? So we can learn things about, and these are both examples of like moduli spaces, right? So the points in these space literally correspond to other objects, right? It's a geometric object that parameterizes other objects we care about. Right? This is like the collection of all the lines through the origin, for example. And so, we can deal with these things like geometrically, and that's cool. Well, I mean, these things are manifolds though, right? So we can already build up that theory, no problem. They're smooth manifolds. We can use those sort of things to study these sorts of structures. And we have questions about like ways that different subspaces might intersect with each other, right? I mean, so like linear algebra is very much about like that can be very much applied, and you might want to know things about how different subspaces intersect, because that is, that has something to do with like simultaneous solutions to different sets of equations. But of course, now we also want to study, like, there are also finite fields, we might want to study, right? And in particular, like finite fields are very useful, or like that's something that can actually be easily implemented on a computer or something, right? I mean, finite fields are everywhere in like algebraic coding theory that makes it possible to like send text messages and stuff like that. So now we would, we still want to know things about like subspaces of vector spaces over finite fields, but now we don't have the access to the same, like humans are very visual, so it's nice if we have a geometric interpretation for these things. How do we interpret these things geometrically, though? Because now we don't have the real or complex numbers. We don't have the smooth varying structure. And this is something that the concept of a scheme allows us to do. It allows us to interpret these objects as being some sort of geometric objects. It allows us to interpret these in terms of geometry, and in particular, it allows us to then prove those geometric statements using algebra. So I don't know. That's just one possible way. That you could look at what the point of one problem that's solved by introducing schemes. Yeah. One last one before you go. Let S be a set and F be a function, be associative and commutative. Furthermore, F has a neutral element. And let S and T be two elements that have inverses. Show that F S T has inverse if and only if the inverse is equal to does that make sense though? I mean, so we're saying if it has an inverse, then it's equal to that? I don't understand the if and only if though. I mean, because the statement in the second part of this, like, instantaneously implies this. So I'm not so sure. Hello, Fimno. Definitions in algebraic geometry are really weird. I agree with that. So also I see your comment. Doesn't that just come from the topology of those spaces? Well, what do you mean by the topology of those spaces? What do you mean by the topology? What is the topology on those spaces? And the thing is, schemes allow you to, those give you a topology on those spaces. A fairly meaningful topology because it's tied into like the actual algebra of these things. So I mean, yeah, that you're right, but that's kind of the whole point. It's like, how do we talk about a topology on these spaces? Definitions in algebraic geometry, I agree they're really weird. But here's why I do recommend that people learn differential geometry first, because like a lot of those, this is not the first time I said this on the stream, a lot of times there's things where it's like, okay, there's this concept that works in differential geometry, but that literal definition that we normally take does not work in algebraic geometry. However, there's often a weirder thing, which is normally equivalent to it, in differential geometry world, and that thing happens to work in algebraic geometry. So, for example, in differential geometry, you can view the tangent space as derivatives of functions from some like small interval into your manifold. that doesn't make sense in algebraic land. But it does turn out that, you know, you have your sheaf of rings on your manifold, and if you look at the stock, at some point this will be a local ring with a maximal ideal, and it turns out that the tangent space is actually isomorphic. Unless I've done things wrong, it's isomorphic to the dual of this quotient. Okay, that's a very weird thing, but the benefit is that this makes sense. It's equivalent to the analytic definition, but it makes sense purely algebraically. Or, for example, you know, there's the definition of the fundamental group of a ordinary topological space, which, you know, this is just homotopy classes of loops based at some point. Again, that doesn't really make sense in algebraic geometry world. You can't really do homotopy classes of paths. However, you realize that the fundamental group is isomorphic to the group of automorphisms of the universal cover. And it turns out that you can still make sense of covering maps in algebraic geometry. And so, and by the way, so in ordinary topology, at least for a sufficiently nice topological space, your cover exists, but it's also a limit of over all the subcovers. And so you may not have a universal cover in algebraic geometry land, but you can still take the limit of all the covers that do exist. And that is exactly why the étale fundamental group is defined how it is. They want you to prove that intuitive statements like they usually do in math and real analysis. Is this an intuitive statement? I don't even know. Are you sure that you wrote it down correctly? Because I'm not sure that makes sense. Like, I would say, yeah, I don't know. Maybe prove that if this is invertible, then its inverse must be this. That's the direction. But I'm actually almost all out of coffee, so I don't think I'm going to touch on this in today's office hour. You don't need Zariski or schemes to define the topology on FPN. On any topological field, it's naturally inherited from the topology on the field. Yeah, I mean, I guess you could view, you know, put the discrete topology on this field, but then probably you just get the discrete topology on these sets, and that's probably not very meaningful. Yeah, I don't know. I'll have to think of a better way to pitch schemes to you and the problems that they solve. Because I also don't really, I'm just like, yeah, schemes are cool. I mean, it's maybe easier to motivate varieties than schemes, but there are things you can do with schemes that you can't do with varieties, right? Yeah. Your main question is how you come about proving that if f has an inverse. Okay. Yeah, I'll just say. I mean. So. You know. Suppose. I would say suppose. So do this. Suppose FST is invertible, right? Then you know that you want to prove that this is its inverse, right? So then what you need to do is basically multiply these two things together and show that you get out the neutral element. So what you'll need to do then is just use properties that you were told about this multiplication, right? So I think you said something about associativity and commutativity or something like that. So use those properties to rewrite this expression a bunch of times until you get one. Do I know about curve counting in enumerative geometry using mirror symmetry? Not really. I mean, I know about curve counting in enumerative geometry. I went to a summer school on mirror symmetry once, but I definitely don't know much about putting all of those things together. Such as rational curves in K3 or so, no. Same way RPN is naturally topological without schemes involved. Well, but again, what do you mean? What do you mean by that? Like, yeah, RPN does inherit, but that's the whole point. Like you can describe RPN as a topological space. Yes, somehow it's inherited from the field, but ultimately, like, the structure that you get is a manifold or like a topological space. And in particular, like, there are tools, like, if you want to do stuff with like intersection theory and intersection of subspaces, there are tools that are just inherently like algebraic geometry in nature to solve those things. But I'm out of coffee, so we'll have to come back to this. I mean, I probably won't have time to do homework on a good motivation for algebraic geometry. But I would challenge you to do some homework, and I would challenge you to go find some historical accounts of how and why scheme theory is useful. Because I guarantee you someone's already written a way more convincing exposition than what I'm going to be able to pull out of my butt in these office hours. Yeah. So that is all for today. Go prove some theorems.